Today's video will be about the Epr paradox and how it is used in quantum cryptography. There was an article that brought forth matters about this Epr paradox, and it was called "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" It was published in 1935. This paper prompted a reprise by Niels Bohr, which he published in the same journal, in the same year, using the same title. There followed a debate between Bohr and Einstein about the fundamental nature of reality. Einstein had been skeptical of the Heisenberg uncertainty principle and the role of chance in quantum theory. But the crux of this debate was not about chance, but something even deeper. Is there one objective physical reality which every observer sees from his own vantage? Einstein's view. Or does the observer co-create physical reality by the questions he poses with experiments? Bohr's view. The original Epr paradox challenges the prediction of quantum mechanics that it is impossible to know both the position and the momentum of a quantum particle. This challenge can be extended to other pairs of physical properties. Suppose we have a source that emits electron-positron pairs, with the electron sent to destination A, here, where there's an observer named Alice, and the positron sent to destination B, here, where there is an observer named Bob. According to quantum mechanics, we can arrange our source so that each emitted pair occupies a quantum state called a spin singlet. The particles are thus said to be entangled. This can be viewed as a quantum superposition of two states, which we call state 1 and state 2. In state 1, the electron has spin pointing upward along the z-axis, or positive z. And the positron has spin pointing downward along the z-axis, negative z. In state 2, the electron has spin negative z, and the positron has spin positive z. Because it is in a superposition of states, it is impossible, without measuring, to know the definite state of spin of either particle in the spin singlet. Alice now measures the spin along the z-axis. She can obtain one of two possible outcomes, positive z or negative z. Suppose she gets positive z. In this case, if Bob subsequently measures spin along the z-axis, there is a 100% probability that he will obtain negative z. Similarly, if Alice gets negative z, Bob will get positive z. There is, of course, nothing special about choosing the z-axis. According to quantum mechanics, a spin singlet state may equally be expressed as a superposition of spin states pointed in the x direction. So suppose that Alice and Bob had decided to measure spin along the x-axis. We call these states 1a and 2a. In state 1a, Alice's electron has spin positive x and Bob's positron has spin negative x. In state 2a, Alice's electron has spin negative x and Bob's positron has spin positive x. Therefore, if Alice measures positive x, the system collapses into state 1a and Bob will get negative x. If Alice measures negative x, the system collapses into state 2a and Bob will get positive x. Whatever axis their spins are measured along, they are always found to be opposite. This can only be explained if the particles are linked in some way. Either they were created with a definite spin about every axis, a hidden variable argument, or they are linked so that one electron feels which axis the other is having its spin measured along and becomes its opposite about that one axis, an entanglement argument. Moreover, if the two particles have their spins measured about different axes, once the electron's spin has been measured about the x-axis, and the positron spin measured about the x-axis deduced, the positron spin about the z-axis will no longer be certain, as if A, it knows that the measurement is taking place, or B, it has a definite spin already about a second axis, a hidden variable. However, it turns out that the predictions of quantum mechanics that there has been confirmed by experiment cannot be explained by any local hidden variable theory. In quantum mechanics, the x spin and z spin are incompatible observables, meaning the Heisenberg uncertainty principle applies to alternating measurements of them. A quantum state cannot possess a definite value for both of these variables. Suppose Alice measures the z-spin and obtains positive z, so that the quantum state collapses into state 1. Now, instead of measuring the z-spin as well, Bob measures the x-spin. According to quantum mechanics, when a system is in state 1, Bob's x-spin measurement will have a 50% probability of producing positive x, and a 50% probability of negative x. It is impossible to predict which outcome will appear until Bob actually performs the experiment. So here's the paradox. One might imagine that when Bob measures the x-spin of his positron, he would get an answer with absolute certainty, since prior to this he hasn't disturbed his particle at all. But it turns out that Bob's positron has a 50% probability of producing positive x and a 50% probability of negative x, meaning the outcome is not certain. It's as if Bob's positron knows that Alice has measured the z-spin of her electron, and hence his positron's own z-spin must also be set, but its x-spin remains uncertain. Put another way, how does Bob's positron know which way to point if Alice decides, based on information unavailable to Bob, to measure x, i.e. to be the opposite of Alice's electron spin about the x-axis, and also how to point if Alice measures z, since it is only supposed to know one thing at a time. So the Copenhagen interpretation rules that the wave function collapses at the time of measurement, so there must be action at a distance, entanglement. Or the positron must know more than it's supposed to know, hidden variables. It is one thing to say that physical measurement of a first particle's momentum affects uncertainty in its own position, but to say that measuring the first particle's momentum affects the uncertainty in that position of the other is another thing altogether. Einstein, Podolsky, and Rosen asked, how can the second particle know to have precisely defined momentum but uncertain position, since this implies that one particle is communicating with the other instantaneously across space, sometimes faster than light. This is the paradox. Most physicists today believe that quantum mechanics is correct, and that the EPR paradox is a paradox only because classical intuitions do not correspond to physical reality. How EPR is interpreted regarding locality depends on the interpretation of quantum mechanics one uses. The EPR paradox has deepened our understanding of quantum mechanics by exposing the fundamentally non-classical characteristics of the measurement process. Before the publication of the EPR paper, a measurement was often visualized as a physical disturbance that had to be inflicted directly upon the measured subsystem. For instance, when measuring the position of an electron, one imagines shining a light on it, thus disturbing the electron and producing the quantum mechanical uncertainties in its position. Such pat and inconvenient but unhelpful explanations of quantum mechanics remain commonplace today, but they fail to explain, among other things, the EPR paradox, which shows that a measurement can be performed on a particle without disturbing it directly, by performing a measurement on a distant entangled particle. Technologies relying on quantum entanglement are now being developed. In quantum cryptography, which we will discuss later, entangled particles are used to transmit signals that cannot be eavesdropped upon without leaving a trace. In quantum computation, entangled quantum states are used to perform computations in parallel, which may allow certain calculations to be performed much more quickly than they ever could be with classical computers. So that's the EPR paradox. Now on to what is quantum cryptography. Cryptography is the process of encrypting data, or converting plain text into scrambled text so that only someone who has the right key can read it. Quantum cryptography, by extension, simply uses the principles of quantum mechanics to encrypt data and transmit it in a way that cannot be hacked. While the definition sounds simple, the complexity lies in the principles of quantum mechanics behind quantum cryptography, such as the particles that make up the universe are inherently uncertain and can simultaneously exist in more than one place or more than one state of being. 2. Photons are generated randomly in one of two quantum states. 3. You can't measure a quantum property without changing or disturbing it. And 4. You can clone some quantum properties of a particle, but not the whole particle. All these principles play a role in how quantum cryptography works. So quantum cryptography, or quantum key distribution, uses a series of photons, we'll start here, which are light particles, to transmit data from one location to another over a fiber optic cable. By comparing measurements of the the properties of a fraction of these photons, the two endpoints can determine what that key is and if it is safe to use. So break this process down further, maybe we can help explain a little bit better. The sender transmits photons through a filter, or a polarizer, which randomly gives them one of 4 possible polarizations and bit designations. There's vertical, horizontal, 45-degree right, or 45-degree left. The photons travel to a receiver which uses 2 beam splitters, horizontal vertical one and a diagonal, to read the polarization of each photon. The receiver does not know which beam splitter to use, for each photon has to guess which one to use. Once the stream of photons has been sent, the receiver tells the sender which beam splitter was used for each of the photons in the sequence they were sent, and the sender compares that information with the sequence of polarizers used to send the key. The photons that were read using the wrong beam splitter are discarded, and the resulting sequence of bits becomes the key. If the photon is read or copied in any way by an eavesdropper, the photon state will change. The change will be detected by the endpoints. In other words, this means you cannot read the photon and forward it or make a copy of it without being detected. If an eavesdropper, let's say Eve, tries to listen in on the conversation, she has to read each photon to read the secret. Then she must pass that photon on to Bob. By reading the photon, Eve alters the photon's quantum state, which introduces errors into the quantum key. This alerts Alice and Bob that someone is listening and the key has been compromised. So they discard the key. Alice has to send Bob a new key that isn't compromised, and then Bob can use that key to read the secret. To read more about quantum cryptography, please read this article in Popular Science magazine. I hope you enjoyed this discussion of Epr Paradox and quantum cryptography.